Hello, everyone. Thank you so much for tuning into this talk on YouTube. Thank you to the organizers for inviting me, and thank you to the organizers of the whole conference. Nearly Carbon Neutral is really great. I'm very happy to participate this year. So my name is Miriam Kuzbary. Today I'm going to be talking to you about joint work with Matt Hedden. The title of my talk is Defining a Best Link Concordance Group. So those of you who have known me for a while have probably heard me talk about this project before, and maybe I'll begin for those people by saying that, this project started a while back and sort of split off into some other things, and we've kind of come back to this recently. So I'm excited to tell you about how we've come back to this project and the progress that's been made on sort of offshoot projects since then. So because I want this to be accessible to everybody, especially graduate students, thanks for listening, I want to set the stage with some definitions first off. So where I'm going to start is I want to tell you or remind you, if you already know, that we say that two knots, K and J in S3, are concordant if... So I'm going to draw a little schematic picture for you here too. So let's say this little box is a picture of S3 cross I. So we have S3 cross 0 at the top and S3 cross 1 at the bottom. And so let's say that we have two knots, K, and maybe J is over here. And we say that these two knots are concordant if there exists a smooth, properly embedded annulus maybe I'll call it C. So properly embedded annulus, taking K to minus J. So I guess I should say that this is minus J if you really think hard about orientation, that's going to be. And a concordance is, like I said, smooth, proper embedding of an annulus. So it could be kind of weird and gross, but, it doesn't have to just be a product, but, it's still smooth, it's still nice. So two knots are concordant if we have a concordance between them. And then we say that two links, maybe I'll call them L and N, classic N for link, in S3 are, so we have actually a couple of different notions of concordance for links, and this will actually come up in my talk, so I want to be very careful about this. So we say that two links are strongly concordant if their components are concordant by disjoint concordances. So maybe here's another little schematic picture. So strong concordance, links have to have the same number of components, and we need, individual concordances between their components, which are disjoint. So that's strongly concordant. And weakly concordant is maybe a little easier. So two links that have different numbers of components can actually be weakly concordant. All you need is a smooth, properly embedded genus 0 surface. So you could have like a pair of pants connecting a two-component link and a knot, for example. So that's what weak concordance means. So maybe before I get into how you can use these ideas to define a group, maybe I should hopefully try to convince you, why should we care about having a link concordance group? For those of you who already think about the not concordance group, maybe you're very happy with that. Why do we need more? So why should we care about having a link concordance group? Well, maybe one reason, again, this is the Floor and Kavanagh homology session, so we like invariants over here, and maybe, you have some invariants that you really like, and you want to throw them at a group. Or maybe some invariants that you like, or like signature, or like Alexander polynomial. So remember, for a link, there are actually a couple of flavors of Alexander polynomial. You have the single variable one, you have the, the multivariable one, and there's a couple of different ideas there, and then again, Floor homology that categorifies those things. And, maybe I'll just shout out to all this great work that's been done on link invariants and Floor homology. And I'll say there's these whole families of these sliced torus invariants for links that are really, really great. So maybe you like invariants, you want to throw them at a group, or maybe, and this tends to be more the perspective that I come from, you like three manifolds and cobordisms, but the three-dimensional cobordism group is trivial, right? If you were to take oriented closed three manifolds and just look at them up to cobordism, and the appropriate group operation is disjoint union, this is actually trivial, and this was proven by Rockline in 51. So if you really care about three manifolds and cobordisms and you want some group structure there, then remember that Licorice and Wallace, sort of independently in the 60s, showed that every oriented, so everything in this talk is going to be oriented, every oriented closed three-manifold can be obtained by Dane surgery, something called Dane surgery, on a link. So it can be obtained by Dane surgery on a link. And if you don't already know what Dane surgery is, that's fine. It's really not important for the talk, but you should just think there's some way of going from taking a three-manifold and coming up with a link that gives you that three-manifold, or some operation on the link gives you that three-manifold. And it turns out that, so if two links are strongly concordant, then their exteriors are relatively homology cobordant. So maybe another motivation behind thinking about a link concordance group is that the study of links up to concordance, so maybe links up to concordance, is sort of related to the study of three manifolds up to homology cobordism. So this is sort of a big motivator for me as to why you might want such a group. Maybe the natural next question is, how do we construct one? In the not setting, because again, we're trying to get to a link concordance group, but there is a not concordance group. In the not setting, the operation that you take is connected sum. So the connected sum is the group operation. You could define it like this. You could say the connected sum of two oriented knots K and J and S3. Everything is oriented, like I said, is you could think of it as the relative connect sum of S3 with K in it and S3 with J in it. And this turns knots into a commutative monoid. So connected sum turns knots into a commutative monoid. And if you prefer pictures, as I do, here's a picture of the connected sum of two knots. So you can do it purely diagrammatically. This is how you get the not concordance group. This guy, which I'm going to refer to as script C, this is the set of knots modulo concordance with connected sum. This is a group. Now, I want you to notice that the identity in this group is exactly all of the knots which are concordant to the unknot. So K concordant to the unknot. So it's the equivalence class of things that are concordance to the unknot. And maybe a good exercise for y'all, if you want to play around with this stuff, is, we say that a knot in S3 is slice if it bounds a smooth, properly embedded disk in B4. So the exercise that is maybe useful to do is show that K in S3 is slice in B4 if and only if K is concordant to the unknot. What can you do with this? If you have a commutative monoid, you can always turn it into a group. You could think of this as the group completion, but it has a fancy name. So what we can do is we can turn any commutative monoid, maybe I'll call it M plus, into a group sort of formally. So if the monoid is M, I'll refer to the Grothendieck group of that monoid as Km. And the way you do it is sort of how you would expect to do it formally. So one way you could do it explicitly, though there's a universal property version. You take the direct product, M with itself, mod out by an appropriate equivalence relation, and then do the group operation component-wise. And here's what you do, or monoid operation component-wise. And so the equivalence relation is that we say that M1, M2 is equivalent to N1, N2 if there exists a K in the monoid such that M1 plus N2 plus K is equal to N1 plus M2 plus K. So here's another nice exercise for y'all, is to prove that the not concordance group is actually exactly what you get if you were to take the Grothendieck group of the monoid of knots. So maybe I'll say knots with connected sum, so that's a commutative monoid, and you just mod out by the subgroup generated by slice knots. And so maybe a big warning here, if we want to, we just formally constructed the not concordance group, right? Let's throw inverses in there, get rid of slice knots, we're done. But if we want to do this in the link setting, it doesn't really work. So a big warning is that connected sum of links is not well defined. So is not defined. Even on concordance classes, even if you orient and order things, it's just not defined. So the idea here for constructing a link concordance group, because we're not the first people to do that, but I hope to convince you that we're trying to get at sort of a natural one to look at. So the idea here now is to choose a different group operation. I want to show you kind of the landscape of what you get when you do this, and then where Matt and I have been going with this. So what you want, you have a set. You have a set of links modulo, maybe let's say strong concordance, because that's something that has this very geometric topological meaning, about the exteriors. So what you can do is you can consider the group operation disjoint union, which is what Hosokawa did. He was sort of the first person to think about this. And if you look at the dates, Fox-Milner is 66, Hosokawa is 67. This is happening around the same time. So if you look at links, you mod out not by concordance, but by these special cobordisms I'm not really going to tell you about, and you take the operation disjoint union, you do get a group. But the problem is that this group is really just isomorphic to the not concordance group, connect some, a copy of the integers. And this copy is just generated by the hop link. So if you think about it, it's really not capturing just how complex links are. The sort of next attempt at this is to instead of looking at links, cut open links on a disk and then stack them like you would braids. And I'm not going to get into that, but if you really want to know more about this group, which is defined by Liddy May in 88, it's called the string link concordance group, I'll say watch my other nearly carbon neutral talk if you would like to learn more about that. And the last one I should mention, so this is a surjection. So this group is actually significantly bigger than the set of links modulo concordance. I should mention that Donald and Owens in 2012 also defined a link concordance group where they still did connected sum, and they fixed a component to connect sum at. It's a really great paper. But I should mention, if you look at everything over here, these notions are actually enlarging the sum of links. They surject onto the set of links, but they're actually bigger. So what we wanted to do is try to figure out, okay, is there a link concordance group where the structure is definitely not coming from how we're choosing to represent the links, or is hopefully not coming from how we choose to represent the links. So this is kind of where the floor homology comes in. So I want to remind you that whenever Ojvath and Szabo were first defining floor homology, when they defined the floor homology of a link, they actually got a connected thing instead. So here's what I mean. So Ojvath, Szabo, 04. they have this procedure where they took an n component link, L in S3, and returned a knot. But here's the thing, a knot in a different 3-manifold. So this is called the notification of the link. So returned a knot in S1 cross S2. And I won't describe the procedure, but I'll just give you a little picture, because this is an example that I really like. It kind of, illustrates a few things that we'll see later. That you can take the hop link, and then when you notify, this is what the notification looks like. So here's the point looking at these things. Well, the floor homology, the knot floor homology of a link was originally defined as actually the knot floor homology of this knot inside the connect sum of n-1 copies of S1 cross S2. So that's one reason that you might care about this object. Really, when you're doing floor homology, you're talking about it. And HFK hat of L categorifies the single variable Alexander polynomial of the link. Sort of a geometric way of looking at that categorification. Okay, great. So if we look at these things, which there's, hopefully you believe me that there's reasons to look at these, you can define connected sum of this, right? The big problem with connected sum of links was that a link is not a connected 1-manifold, but now we have these connected things. So for 2 notified links, maybe in different copies or different numbers of copies of S1 cross S2, you do have to keep track of how many of those you have floating around. You can now define their connected sum. So we can define the connected sum of 2 notified guys, or really 2 knots in sums of S1 cross S2, as the relative connected sum, again, of this guy with kappa L1 in it, connected sum with this guy with kappa L2 in it. And notice that this is going to give you a knot inside a connected sum of n plus m copies of S1 cross S2. So we have a commutative monoid now. And to save myself having to write it every time, I'll write it here as m. So limit, direct limit, because you gotta have this direct limit because now the number of copies of S1 cross S2 is changing. So set of notified links in n copies of S2 cross S1. If you wanted to, you could just look at all knots, but we're going to focus on links because in context here. And so this is an abelian monoid. So now you could run the same trick that we did for knots in S3. So construct a link concordance group this same way by taking the monoid generated, or taking the Grothendieck group of M and then dividing by, or modding out by the subgroup generated by slice notified links. Now, at this point, you might be getting kind of upset with me because what does slice mean here? And this is the problem. Slice in which 4-manifold? We got to say, right? And what you should notice is that, if you want to explicitly construct inverses by doing this, if you know the knot concordance group really well, and you think about that procedure, so if we want to construct inverses explicitly, then really we need to know, so if we want to construct an inverse explicitly, we sort of need a notified link and whatever, when I say minus KL, I really mean formally. So in the Grothendieck group, we really need this to bound a disk, and the boundary connect sum, let's say this is in n copies of S2 cross S1. We really need this to bound in n copies of S2 cross D2, connect sum n copies of B3 cross S1. notice that if you bound in a boundary connect sum of S2 cross D2s and B3s cross S1s, you can always sort of isotope away from the B3 cross S1 factor enough to do surgery and just get a disk in only S2 cross D2s. Here's the problem. Bounding in S2 cross D2 is like kind of a weak thing. So there's this fact, so Davis, Nagel, Park, Ray, they have some examples. I have some examples. We use pretty significantly different techniques, and we're working on these kind of ideas around the same time. But there exist knots in connected sums of S2 cross S1s, which are slice in a boundary connect sum of S2 cross D2s, but are not concordant to the unknot so concordant to the unknot in S2 cross S1 times I. And if you notice, I'm kind of suppressing this fact that you could take the same knot and you could sort of connect some on more copies of S2 cross S1 away from the knot, but you can still show, even if you do this stabilizing kind of thing, it's still not concordant to the unknot. And maybe here's this example again, the notified hop flink. And you can, this one you can see is an example of this using a few different ways. So let me show you first the disk that it bounds in S2 cross D2. So here's part of it behind. And then here's another disc in front, and then they're connected by this twisted band. And maybe I'll darken this up here so you can really see that this is in front. So there's your disc, and you can see that it's not concordant to the unknot using a few different ways. You could use signature, you could use the Schneiderman self-intersection invariant mu. If you want, just because I'm going to shamelessly plug myself, you could use the Dwyer number that I defined. It's maybe more complicated a tool than you need for this example. That's more useful for a little more subtle, difficult examples. Unfortunately, this is much weaker than actual concordance in S2 cross S1 cross I, and we can still study it. We can still go forward with it. So here's another project that sort of split off from this. So Hedden and Rayox posted this on the archive last year as part of their relative adjunction inequality paper, which is great, and you should read it if you haven't already. But they showed that for an n, as a consequence of their work, that for an n-component link L in S3, there's a family of tau invariants that give you genus bounds on 4 manifolds bounded by your notified link. So in particular, each tau, the absolute value, gives you a lower bound on the genus and combinations of S2 cross D2 and B3 cross S1. And using these taus, you can actually get a homomorphism to Z. You can get a surjection to Z if you define this as what slice means for notified links. But the problem is, again, this maybe is too weak of a notion. So maybe slice in S2 cross D2s is too weak of a notion. And we get this map to Z, but we didn't really get much else. And so, okay, great, you have a map to Z, but what else is the structure of this thing? And maybe I'll also say that inverses are really hard to construct explicitly because unlike S3, a connect sum of S2 cross S1s has non-isotopic orientation reversing diffeomorphism. So inverses become kind of gross. And so this is where we picked this back up recently and trying to get at a better notion of notified link concordance group. So maybe a couple of observations is that if you have that L1 and L2 are strongly concordant, so maybe I'll leave this blank here, L1 and L2, if they're actually concordant in S3 cross I, if they're strongly concordant, that actually implies that their notifications are concordant. So strongly concordant, kappa L2 are concordant in, let's say they're n component, so their notifications are concordant in n-1 copies of S2 cross S1, cross I. So strongly concordant implies the notifications are concordant, but the other direction actually doesn't work. But what is implied is that if you have notifications concordant, then that means that any links that give you those notifications are actually weakly concordant in S3 cross I. So knowing that, and knowing that if you think about it, the connected sum of, actually, hold on, sorry, let me finish writing this. So if you look at a notified link in n copies of S2 cross S1, and then you take the disjoint union of that with another knot inside m copies of S2 cross S1, this is actually sort of cobordant. Not sort of, this is cobordant by a very simple cobordism to the connected sum of n plus m copies of S2 cross S1, and then this connected sum of the notifications inside that 3-manifold. So I want to show you a picture to illustrate this cobordism. So maybe here on the left, you see schematically, even though these are very simplified, obviously, pictures of these two different 3-manifolds with these two different notified links in it. And then here's the single 3-manifold over here. Well, these are cobordant in a really nice way. So the 3-manifolds themselves, if you think about it, the way you get from the left to the right is you just add a single 4-dimensional one-handle. And if you look at what's happening inside that cobordism, you also have a cobordism between the knots where you just added a single 2-dimensional one handle. So you have these sort of nested pants connecting these guys. So this was sort of the inspiration for trying out something different recently. And so this is the direction we've been going, that maybe a better notion that sort of preserves a little more of what's going on is to look at connect sums of S2 cross S1 with a notified link in them and the group operation of disjoint union, but we're, taking these disjoint unions of these separate manifolds, and then what we're doing, that's a monoid, mod out by the subgroup generated by co-bounding, knots that co-bound an oriented genus 0 surface with the unknot in a 4-manifold with only 1 and 3 handles. And so really what we want to do, if you remember way back when I first told you about the landscape of link concordance groups, there's a lot over here, and there's a lot of really good work that's been done on Letty May and Donald Owen's groups that enlarge the set of links, but over here there's not much. There's really just this Hosokawa group. So our conjecture is that if you construct the group this way, that you will actually get a link concordance group, which is not just isomorphic to the Hosokawa group, which, just to remind you, this was very simple. This was just the not concordance group connect sum, a copy of Z generated by the Hopf link. So maybe where I'll end, because I know I'm about out of time, is try to use these some adapted intersection invariants. Is really what we want. We don't just want to map to Z, we want to map to much more than just the Z. And obviously, floor homology kind of plays nice with the cobordism maps that you get from just adding 1 handles and 3 handles. So maybe another avenue that we need to explore more is trying to get some results using the not floor homology of these links. So that's about out of time. Thank you for watching.